Welcome to qnawire.
All right, so in this problem, we have to find the smallest and largest speed at which a car can move around a banked curve without relying on friction. Now, I've drawn the free body diagram for this banked curve problem here. As you can see, we have a gravitational force pointing downwards, as well as the normal force pointing perpendicular to the surface. What's interesting here, however, is the components of the normal force. We have the vertical component pointing upwards, as well as the horizontal component pointing inwards towards the center of the motion. Now, knowing that this right here is our angle theta, we can set up some relationships between these values. First of all, we can see that Fn cos theta is equal to the gravitational force, since this is the force that is pointing straight up and therefore canceling it out. That means that we have an equation for our normal force, mg over cos theta. Now, as we know, the horizontal component of the normal force is what allows us to move around a banked curve without there being any friction. So Fnx, since it's pointing towards the center of the circle, is mv squared over r. And that is also equal to Fn times the sine of theta, as we can see from our diagram here. All right, so we know what Fn is equal to. It's mg over cos theta. So that means that Fnx must be equal to. That means that if we plug in mg over cos theta times sine theta equals mv squared over r, we get that mg tan theta equals mv squared over r. Now we want to solve for velocity, and we have that in terms of known quantities now. So we can say that v is the square root of rg tan theta. Let me make that r a little bit cleaner. All right, well, how do we know what tan theta is? Well, let's go back to our drawing. We know that the height of this banked curve is 18 meters, as you can see here. And for the first part, when we're looking at the smallest possible velocity at which the car can move around the curve with, we're going to be looking at the difference between these two radii, 165 and 112. So that means that because tan theta is the opposite over the adjacent side, we're going to have rg times 18 over 165 minus 112. So now we can plug in and we get that v is going to be equal to 9.8 meters per second squared times 112, which is the radius for when we are moving with the lowest possible velocity, so right by the edge, the lower edge of our curve, times 18 over 53. And that's going to give us an answer for the first part of our problem of 19.307 meters per second. So that's going to be the smallest possible velocity at which we can move around the curve with. Now let's look for the greatest possible velocity. We're going to use the same equation, v is equal to g times r times the tangent of theta. So once again, we're going to plug in our known quantities, 9.8 meters per second squared times, and now we have to look at our radius. So the highest possible velocity is always going to be at the very upper edge of the curve, so that's times 165. And that's going to be multiplied once again by 18 over 53, our tangent theta. And that's going to give us a result of 23.434 meters per second. And so that's going to be the answer to the second part of our question, which we can round to roughly 23 meters per second. So now we have two values. Our lowest speed is about 19 meters per second rounded, and our highest is 23 meters per second rounded, and that's the final answer.